Welcome back to the Quantum Rings Quantum Summer School. So far in this course, we've only worked with perfect qubits, but today is all about noise and errors. So the first thing we're going to talk about is some different types of real-world qubits, so mainly focusing on neutral atoms and superconducting qubits. And then we're going to explore different types of qubit errors and decoherence. And finally, we'll talk about some error mitigation techniques. Let's get into it. So today we're going to start off by first talking a little bit about real-world qubits, and I'm going to give us two examples of current quantum computing architectures, neutral atoms and superconducting qubits, so a little background on what those are and how they work. Then we're going to talk about decoherence, so how qubits lose their quantum information, as well as errors, and then we'll talk a bit about error mitigation techniques. So we want to make qubits, and one thing that we might want to think of is what are the properties of a good qubit? Well, the first property is that it ought to be a quantum two-level system, because there should be two states, which we can assign the 0 state and the 1 state. So our state is some superposition of two basis states, 0 and 1. And it doesn't really matter what these two states are, it just needs to be a well-defined two-level quantum system. We also need the qubit to be able to be manipulated so that we can perform gates. So somehow we have to interact with the qubit in order to perform gates. And then finally, we want it to maintain its quantum information for as long as possible. So the longer it maintains its quantum information, the more gates we can do, the larger computation we can do. And the time that it maintains its quantum information is called the coherence time. So what kinds of things contribute to reducing the coherence time? So one thing is losing energy to the environment. So you have your qubit and it's coupled to the environment in some way, and that's a lost channel. Energy can be lost from the qubit to the environment. You can also have imperfect gates that add noise. So for instance, you could have a gate that applies a slight over or under rotation, more or less than you would expect. And then there's also other factors like material defects that could couple to your qubit, or magnetic field fluctuations in your lab that impact your qubit, or even cosmic rays, which when they hit a qubit can cause it to change its state. There's a few different promising quantum computing architectures. So one is arrays of neutral atoms, another is superconducting qubits, there's also trapped ions and photonic quantum computing. And arguably, neutral atoms and superconducting qubits are two of the most promising directions. I personally work with superconducting qubits. So we spent a lot of time so far in the course just taking a qubit as a very abstract thing. And I want to take a little bit of time here to talk about what an actual qubit looks like. And I'm going to use as the two examples a neutral atom qubit and a superconducting qubit. So first, for a neutral atom, the basic principle behind this is that atoms have discrete energy levels. So you may have heard before about electron orbitals. So in an atom, electrons can only exist in certain discrete energy states. So for instance, there's like sp and d orbitals and like other orbitals as well, but you can't occupy anything other than these orbitals. A consequence of that is that atoms also have a discrete emission spectrum. So for instance, the emission spectrum of hydrogen looks something like this, where these are the wavelengths of light that hydrogen can emit. And each peak in the emission spectrum corresponds to an allowed transition between two electron orbitals, or energy levels. And only certain transitions are allowed. So the basic premise behind a neutral atom qubit is to choose an atom with a well-protected transition. So a transition that has a really long lifetime because it's pretty well uncoupled from the environment. And usually people choose Rydberg atoms. So for some examples of that would be rubidium and ytterbium. Then what you're going to do is you're going to trap the atoms in optical tweezers. And an optical tweezer is just laser beams that are really tightly confined down to essentially a single point. You trap an atom with that really finely constrained laser beam. And then finally, you're going to use laser beams to communicate with your qubit to apply gates. So essentially, you'll use laser pulses to apply gates. Some strengths of the neutral atom platform. So one is that they're pretty long coherence times, so on the order of seconds. This is because these transitions in the atom, there's two energy levels, is pretty well uncoupled from the environment. And so if you put an electron into that well-protected transition, it's generally not going to decay out of those two levels. The other nice thing is that every qubit is identical. So atoms are made by nature and each one is the same. This is not true, for instance, with superconducting qubits. One weakness that neutral atoms have is slow gate times. So this kind of goes hand in hand with the long coherence time, but because the two levels in the atom don't interact much with the environment, it also means that it's hard to interact with them to perform gates. So the gates are going to be slow. And then also readout is destructive. So when you try and measure your qubit and learn what state it's in, there's a high probability that the atom will be lost from the optical tweezer, the trap. So you can't read out your qubit and then continue to use it. The idea behind superconducting qubits is to make an artificial atom. And the reason for this is so that you can engineer the properties of this atom in ways that are beneficial or would be useful. So to start off with, we can think about the concept of an LC circuit. So L is like the letter usually used to represent an inductor, and C is the letter used to represent a capacitor. And this is a simple oscillating circuit. You may have seen this if you ever taken electromagnetism or been in a class where you build circuits. And you can think of it as the charge or the current oscillates back and forth between the capacitor and the inductor. And in the quantum limit, just like with atoms, there are only discrete energy levels which are allowed. So it can't just oscillate at any frequency. There's certain discrete frequencies that are allowed, which correspond to energies. And we call this the quantum harmonic oscillator. And the potential energy well of the quantum harmonic oscillator, where this x-axis is the phase across the inductor, which is not super important. The important part is that these energy levels are evenly spaced by h bar, which is Planck's constant, divided by 2 pi times its characteristic frequency. So there's a slight problem here, which is that we know that our qubit needs to be a two-level system, so we can have a 0 state and a 1 state. And here, let's say we picked the bottom state to be the 0 state and the second state to be the 1 state. Then, if we start in the 0 state, we could add a photon into the system, which can be absorbed and excite us up to the 1 state. And that could be a way to apply an X gate. But now, if we're in the 1 state and we apply another photon, there's two things that could happen. So one thing is that there could be stimulated emission, where we decay back down to the 0 state and emit a photon. Or, which is something that we don't want, we could be excited up again to the 2 state. This cannot be a qubit. So to make this into a qubit, what we're going to do is swap out the inductor for a Josephson junction. And a Josephson junction is just a superconducting nonlinear inductor. And this little circuit is called the transmon qubit. Josephson junction is literally just superconducting metal with an insulating gap and then superconducting metal again. And this nonlinearity adds some anharmonicity into the system. So now we have an anharmonic oscillator, and the energy levels now become unevenly spaced, where the gap between the first two energy levels is the largest, and then they get smaller after that. So now we have a well-defined two-level system that we can use, the ground state and the first excited state. And if we're in the one state and we apply a photon corresponding to this frequency, we can't be excited up to the second excited state because it's the wrong amount of energy to add. So the only option is to have stimulated emission back down to the zero state. And the transmon qubit is arguably the simplest superconducting qubit. You can imagine making other types of circuits which are more complicated, and these are other type of qubits. One that's really popular that you might have heard of is the fluxonium qubit. And yeah, basically other types of qubits have certain desirable properties. And that's one of the benefits of superconducting qubits, is you can engineer your atoms to have the properties that you want. So the idea is that we're going to make superconducting electrical circuits, we're going to run control wires next to them, and then we're going to use microwave signals to apply gates. So for our qubits have a characteristic frequency around in the gigahertz range, which corresponds to the microwave regime. Some strengths of superconducting qubits: we can do fast simultaneous gates, so you can apply gates to all qubits at once. And then we also have non-destructive readout. So you can measure the state of your qubit and then it will remain in that state and you could continue to use it. One weakness is low coherence times, because superconducting qubits are pretty strongly coupled to their environment relative to a neutral atom. So that means that they decay and lose their quantum information a lot faster. And then also we're constrained to a fixed layout. So the circuit is laid out as it's laid out, and you can't change the conductivity. With atoms, you can actually shuttle them around, moving the optical tweezers. So you could have two qubits interacting over here and then bring that other qubit to interact with someone else. So that's really helpful for this type of all-to-all connectivity, whereas with superconducting qubits, we only have a local connectivity. Also, superconducting qubits are prone to defects from fabrication. They're all going to be a little bit different from each other because they're circuits and they're all going to be a little bit different from each other. So now let's talk about decoherence. There's two main types of decoherence processes. So the first is amplitude damping. This is when we have our two energy levels for our qubit. One is a lower energy state and one is a higher energy state. Usually this is going to be a ground state and a first excited state. And let's say we're sitting in the excited state. There's going to be a tendency to decay down to the zero state and emit a photon. And the characteristic decay time for this is often called T1. And then the other main type of decoherence is dephasing. And we know that our quantum states can be expressed as cosine theta over 2 times the zero state plus e to the I phi sine theta over 2 times the one state. And that e to the I phi encodes the phase information of our quantum state. And so dephasing is the process of losing this phase information. And the characteristic decay time for this is called T2. We can look at these processes on the block sphere. So let's say you have this state psi, and you want to consider the impact of T1 relaxation. So this is amplitude damping. And that's a tendency to decay back down to the ground state. So maybe after some time, our qubit state has rotated like this, up more towards the zero state. And this would be a T1 process. Then there's also T2 relaxation or dephasing. And this is where we have increasing uncertainty in the phase of the qubit. So now instead of having one well-defined phase, you can think of it as fanning out along the equator. So having more uncertainty in the phase. So this would be a T2 process. There are other common sources of error beyond decoherence. So one would be in state preparation or readout. And these are together usually called spam errors, state preparation and measurement. There's also gate errors. So your gate is supposed to do a perfect 180-degree rotation, but it does a 181-degree rotation, something like that. There's also crosstalk. So you're trying to control one qubit and you actually impact the state of another qubit. There's erasure, so for instance, losing an atom out of an optical tweezer. Erasure is the state is lost entirely, basically. And then there's also correlated errors. So there could be some error that happens simultaneously with two qubits. So now let's move over to the coding notebook to take a look at some of these things. So first we're going to import all the libraries that we need. We're also going to install Qiskit-error. That's mainly what we're going to be using today because it's a really nice way to incorporate noise into your simulations. So this is from Qiskit. And we're going to be using all these different types of errors and noise mechanisms in our simulations today. We have a few helper functions here, so I'll come back to this one when we're using it later, but this is for running a circuit with T1 and T2 decay. And then here's a GHZ state preparation circuit, so remember that this is a state which is like 0, 0 plus 1, 1, but it could be as many qubits as you want, so like 0, 0, 0, 0 plus 1, 1, 1, 1. Yeah. This is a function which tells you the parity, the average parity, given counts dictionary, which is a result from running a measurement. And the parity of a bit string is 1 if the number of ones in the bit string is even, and it's -1 if the number of ones in the bit string is odd. So it just finds the parity of every bit string that was measured and takes the average of that. We're going to use that later in the last part of this. And then there's a Bell state preparation circuit too. So the most basic form of error is a single qubit error, and this is usually incurred during a gate or a measurement. When we talk about T1 and T2 decay, we're normally thinking of that as happening over a period of time. So a bit flip error is going to flip every 0 to a 1 and every 1 to a 0, and then a phase flip error is going to flip the phase of the 1 state. So here's an example of a bit flip error. We're going to start by preparing the Bell state, and then we want some probability of the error occurring, so let's say 5%. And then we model the bit flip error using Pauli error, and then the error is going to be x with probability p. This should be in a tuple, I think. And it's going to be do the identity, so no error, with probability 1 minus p. Then we're going to make a noise model, and we're going to add all qubit quantum error, and we're going to add our bit flip error. And then we have to specify which instructions we want it on. So let's say we want it to happen every time we apply a Hadamard gate. So remember, that's a key ingredient in the Bell state preparation. Then we're going to create a noisy simulator backend with our noise model. We're going to transpile the circuit, and then finally we're going to run the noisy circuit and get our counts. Oops. You should run all of these cells first. Okay, so there's our little circuit, and we can see the histogram of counts, and we can see that we measured 0, 0 or 1, 1 always. And our error didn't really seem to do much, and in fact, it's not going to impact us at all. And can you think why the bit flip error didn't cause any problem? Because after the Hadamard gate, we're in the state 0 plus 1, and so it doesn't matter if we have a bit flip error, it's still the same. So we can see the bit flip error if we have the error happen during the controlled X gate. So here we can have a bit flip error with probability 10%, and then it's going to apply identity on the control qubit, X on the target qubit with probability P, and do nothing with probability 1 minus P. We're going to add this error to everywhere we have a controlled X gate. and then all the rest of this is the same. And now we can see we have around 10% chance of having a bit flip, because there was 1,000 shots and we have around 100-ish that have a bit flip error. We can also have phase flip errors, so we can apply a Hadamard gate, and then putting an identity here, which is where a bit flip error can occur, and then another Hadamard gate. In the absence of errors, you apply a Hadamard and then another Hadamard, you should end up back in the 0 state. But if we have a phase flip error in between, then we're going to get flipped from the plus state to the minus state, and then the last Hadamard will send us down to the 1 state. So we want to have, let's say, a 10% chance of a phase flip, and that's going to be a Pauli error of Z with probability P. And we're going to apply this everywhere we see the identity. And then I've added this optimization level equals 0 here, because if you don't, it will get rid of all the identity gates, because it tries to simplify things. And here we can see that actually exactly 10% of the time here, but that's just by chance, we had a phase flip error. Another common type of error is a readout error. So basically the act of measuring your qubit actually changes the qubit. Let's use the GHZ circuit as our circuit. Maybe let me just draw this so we all know what we're talking about. We're just making the state 0, 0, 0 plus 1, 1, 1. Then we want to have some measurement misassignment probabilities. So probability that we would measure 0 when it was actually in the 1 state, let's say this is 10%, and then probability is we measure it to be in the 1 state given that it was actually in the 0 state. Maybe this is 5%. And then we have to create our error. This is going to be a readout error. So the first part here, this is going to be a matrix, and the first element is going to be the probability that we measure 0 given 0. So that's going to be 1 minus the probability of 1 given 0. And then this other one is going to be the probability of 1 given 0. And then here, that other diagonal is going to be the probability of 0 given 1. And then the last one is the probability of 1 given 1, which is 1 minus P0 given 1. We create our noise model, we add our readout error, and then we can run the circuit. So here we can see that in a perfect case, we should have measured either all zeros or all ones, but now we've had these readout errors and we get a scrambling of all the other possible states as well. So one question you could think of is how you go about characterizing the readout noise for a qubit, and what would be your approach to determine the underlying noise model if you assume that it's this type of noise. Now let's talk about decoherence. So qubits mainly decohere from coupling to the environment. So one way is amplitude damping, where energy is lost to the environment, and the other is dephasing. Usually there's some sort of, for instance, with superconducting qubits, you would have flux noise. So there's some magnetic flux that's causing your qubit phase to gain uncertainty. First, let's try amplitude damping. So here we can have a quantum circuit, and the general scheme for how we're going to do this is we're going to have an X gate to excite us to the 1 state, and then we want to wait some period of time and then see what state we're in, either 1 or 0. And the longer the time is, the more we should have decayed down to the 0 state. So we're going to do an X gate, and then we're going to do the identity gate. And then we need to pick our T1 and T2 decay times. So these are going to be in nanoseconds. And let's say I have 20 T2 can be, 30 microseconds. So we're more dominated by amplitude damping. We can have delays from 0 to 200 microseconds. And then at each time delay, we're going to do 1,000 shots and take the average. And we're going to run a circuit with decoherence with T1, T2, and a delay time. And then we're going to, for each of those, count the population of 0 and 1. So we get something that looks like this, where we start off in the 1 state, and the population of the 1 state drops and decays down to nothing, and the population of the 0 state grows. And this is actually fitted with an exponent. It can be fitted with an exponential, and the function kind of describing this would be like e to the minus t over t1. And when t equals t1, we've decayed to 1 over e times the original value. And that's why it's called the characteristic time. We can also consider dephasing. So for dephasing, our previous scheme would not work because we want to see us losing phase information. When we're in the 1 state or the 0 state, we can't really tell anything about the loss of phase information. So where should we put our quantum state if we want to have the greatest impact from loss of phase information? We should definitely go somewhere on the equator of the Bloch sphere, so those equal superposition states. So we can put ourselves there using an x rotation, pi over 2 on qubit 0. Then again, we're going to wait for some time. And then we can apply another x gate. And there's kind of 2 ways we could do it. We could either apply another pi over 2, and we should end up in the 1 state, or we could do a minus pi over 2 to go back to the 0 state. Well, let's just do another pi over 2. So we want to make sure that we're dominated by T2 loss, so let's just make this really big. And then the T2 is going to be the main decay mechanism. And then here again, we're going to run a circuit with decoherence. We're going to keep increasing the delay time. Basically, thermal noise with T1 and T2 decay is going to be applied for time delay on every identity gate. So what we see is that we have the 0 state and the 1 state kind of decaying down into the middle, and also the 0 state population rising up into the middle. And what's happening here is that actually, if you think about it in the Bloch sphere picture, our quantum state is moving towards the center of the sphere. So if you have not a vector, but just the point at the center of the sphere, that's the classical mixed state. And basically, that state in the middle there is like a coin flip. So it's either, you flip a coin, it's either head or tails. And we know that a qubit is not the same as flipping a coin, because it has that phase information that allows it to have interference effects and other useful quantum phenomena. Without phase, it's really just a coin flip. So T2 dephasing loses that phase information and reduces our qubit to a coin flip. That's also why after the decay, you have a 50% chance of measuring 0 and a 50% chance of measuring 1. Okay. There's a few questions here to consider if you're interested. And last, let's talk about error mitigation. So I talked a lot about how we have so many errors, and this is a huge problem in the field currently because we want to do all kinds of cool algorithms, but we're limited by coherence times and errors. And there's actually a huge subfield called quantum error correction, and we're going to talk about that in episode 13. But a step before that is error mitigation. So just using some techniques to reduce the impact of errors. One example is called dynamic decoupling. So remember that we can think of the dephasing of the qubit state as the vectors fanning out on the Bloch sphere. And the way that the dephasing happens is usually not completely random, but it kind of has to do with how the qubit interacts with the environment. So that means if, for instance, you have some vector that's moving this way at some speed, and all of a sudden we flip the Bloch sphere up on its head, it'd be moving in the opposite direction as it was before at the same velocity. So at some point in time, you would expect that all the vectors again recombine at the starting point before there was any dephasing. And we call this an echo. So this is kind of best to be seen with an animation. I think this is a pretty good one. But here you can see that originally everything is combined, and then they start fanning out, and then you flip the Bloch sphere, and then they start recombining, and then at some point there's an echo where they all are like maximally recombined. So what we're going to do for dynamical decoupling is that halfway through our quantum circuit, or like sequence, we're going to use a pi pulse. That's so that the dephasing in the first half of the sequence cancels out with the dephasing in the second half of the sequence. So basically the echo is happening at the end of the sequence when we're going to measure. And dynamical decoupling reduces the error, but it does not stop it from occurring. So here's the circuit that we're going to use. So we're going to do a similar thing to the dephasing circuit before. We're going to have an X rotation, we're going to have some idling time, and then if we're using the echo technique, we need to apply an X gate, and then we need to apply another rotation. But actually in this case, because we've flipped everything up on its head, we actually want to do a minus rotation. In the other case, we'll do the identity and then the X rotation again. In both cases, in the absence of decoherence, we should expect to measure 1 at the end of the circuit. So now we can consider this case. I made T1 really large, so we're not impacted by amplitude damping at all. And we have our typical T2 decay. And then here, just as like a model of noise, I have some what I'll call coherent phase noise. We have some angles between 0 and 10 to the minus 5 times pi rotation per nanosecond. And then essentially what's happening is there's some like coherent rotation in one direction, and then when we apply the pi pulse, it will rotate back in the other direction and then have an echo. So we can compare the two methods. So one where we're using the echo and one where we're not using it. Oops, I have a typo here. Okay, try that again. Whoa. And also, I forgot which qubit we're applying to here. Hopefully it works now. Okay, so now you can see without the echo technique, we're decaying down, just like we saw before in the previous problem. And with the spin echo technique, some of that error is mitigated. So we decay slower. Eventually though, it will all decay down to the same place. But you can see that there's some reduction in error from using this echo technique. So the last thing I want to talk about today is zero noise extrapolation. So basically, we're going to have some circuit with noisy gates, and let's say we can describe that with unitary U. So in a perfect world with no noise, if we apply U dagger U, that should be the identity and do nothing. But in practice, we would actually have double the noise because we applied all the gates twice. So what we're going to do is we're going to fold in more copies of U so that we amplify the noise even more. And then we can fit the results versus the number of folds and extrapolate to 0. And it's called zero noise extrapolation. So here I've just created some noises. So here we have a coherent error, which is an over-rotation of 2 degrees, which we're going to apply on Hadamard and X gates. We also have depolarizing noise. So this is just decoherence, but you can think of it as instantaneously applied by a gate rather than occurring over time. And then we're going to have our single qubit errors, which is that coherent error and the depolarizing noise. And then we're also going to have 2 qubit depolarizing noise on our controlled X gates. Now the circuit that we're going to use is our GHZ state. And we want to consider different scale factors for noise. So if the scale factor is 1, then we're not going to add any additional gates. We just want to see the bare circuit, like the standard unitary U. For scale factor 3, now we're going to have 3 times the noise because we're going to have U and then 1 fold, U dagger U. And if we add another, we'll have 5 times the noise and then 7 times the noise. And what we're going to be measuring is the average parity at each of these scale factor points. What should the parity of the GHZ state for, let's say, 4 qubits be? Well, for the all 0 state, the number of ones is even, it's 0, so the parity of that is 1. And then for the other one, all the ones, again, that's an even number of ones, so the parity is also 1. So we should expect that the parity is 1 if there is 0 noise. So first we're going to apply our unitary. Then the number of folds that we want to do is going to be our scale factor minus 1 divided by 2. And then we're going to want to apply the inverse of the GHZ circuit. And the GHZ circuit. And at the end, measure everything. So then we get our counts, and then at the end, we want to append that average parity. So let's try it. And then here I'm just performing a linear fit on that so we can see what we measured the parity to be with uncertainty, and then plotting it. So let's see. Okay, so here we can see that we extrapolated back to 0.965 plus or minus 0.02. So that's pretty close to 1. Of course, it's going to be a little bit different every time you run it due to the noise. So some things you can play around with is what happens as you add higher scale factors, what happens with other numbers of qubits for the GHZ state. You can also try this zero noise extrapolation with other types of errors in circuits as well. So hopefully now you've gained an appreciation for the challenges that we have in trying to build quantum hardware. And you can see that we're still a very long way away from what we want to be able to do, which is run really long and complex quantum algorithms. So stay tuned for a few weeks from now, episode 13, we're going to be talking about quantum error correction, which is taking this error mitigation technique to a whole other level where we're trying to build logical qubits rather than try and correct for errors on physical qubits. I'll see you next week.